On behalf of the scientific team, it is a great pleasure to present at the first virtual European Conference on Fracture the study entitled Temperature Dependence of the Luminescence Output of Cadmium Tungstate Crystal in Comparison with Calcium Fluoride Doped Europium Crystal. The scientific team consists of George Saatsakis, Konstantinos Ninos, Ioannis Valais, Nectarios Kalyvas, Athanasios Bakas, Ioannis Kandarakis, George Panayiotakis, and Christos Michail from the University of Patras and the University of West Attica. During the last decades, there is increasing interest in applications of scintillators at harsh environments, such as in geophysical detectors for deep geology boreholes, non-destructive testing of pipelines in oil and gas industry, space and marine exploration, nuclear reactor monitoring, radiation chemistry, etc. Various companies like Saint-Gobain already produce scintillators for harsh environments, such as Polycine, sodium iodide activated with thallium, lanthanum bromide, bismuth germanium oxide, and others. The current study is the first step towards the investigation of the luminescence efficiency dependence of single crystal scintillators over wide temperature ranges. This slide presents some major mechanical properties as shown on the top right corner of the screen. It is also worth mentioning that cadmium tungstate is a scintillator with a long history as an energy converting medium. Also, cadmium tungstate is one of the denser scintillating materials with one of the shortest radiation length. Both crystals under investigation have high melting points, which is a crucial characteristic in certain applications. Both crystals were purchased from Advatech UK Limited and were in single crystal form. Finally, both crystals have dimensions 10 by 10 by 10 mm and their surfaces were polished. Both crystal properties are shown on the table at the right side of the slide. Cadmium tungstate has a high attenuation coefficient, a wide emission wavelength band with the main maximum at 490 nanometers, which is ideal for coupling with a variety of sensors such as photomultipliers and photodiodes. Its energy resolution varies from 7.5 to 8.5% using cesium-137 gamma radiation. Cadmium tungstate is non-hygroscopic, radiation-hard, and also cheap with short afterglow. However, there are certain drawbacks such as the fact that it is difficult to produce in large dimensions and it is toxic due to cadmium. On the other hand, europium-activated calcium fluoride can be easily found in nature and can be manufactured in large quantities with low cost. Europium-activated calcium fluoride is easily machined, offers excellent operational characteristics such as non-hygroscopicity, inertness, insolubility, and thus can be placed in direct contact with solvent systems or aqueous solutions. It has good mechanical properties when used in particle or low-energy radiation detectors, and it is well suited to use within vacuums since it has very low vapor pressure. The experimental setup used during this study is shown on the schematic diagram on the right. The crystals were exposed to X-rays on a BMI General Medical Merate tube with rotating tungsten anode and inherent filtration equivalent to 2 mm aluminum with energies ranging from 50 to 130 kVp. Additional 20 mm filtration was introduced in the beam to simulate beam quality alternation by human body. The light flux measurements were performed using a light integration sphere coupled to a photomultiplier tube which is finally connected to a vibrating reed electrometer. The crystal was positioned at the input port of the integrating sphere, whereas the photomultiplier was adapted at the output port. The photocathode of the photomultiplier was directly connected to an electric current meter. In order to measure the absolute efficiency of the single crystals at high temperatures, a heating gun was used to increase the crystal's temperature to 128 degrees Celsius as shown on the diagram on the left. The crystal's temperature was monitored using an infrared laser digital thermometer. The efficiency of a scintillator to emit light after X-ray exposure can be experimentally determined under clinical conditions by the absolute luminescence efficiency defined in terms of emitted light energy flux per unit of incident exposure rate. This table shows the measured X-ray tube output with the Piranha dosimeter used in our experiments. The luminescence efficiency was found in both cases maximum at the lowest examined temperature, which was 23.06 efficiency units for cadmium tungstate and 22.01 efficiency units for calcium fluoride doped with europium. With increasing temperature, the luminescence efficiency decreased constantly for both crystals due to thermal quenching. That is 5.32 efficiency units for cadmium tungstate and 4.43 efficiency units for calcium fluoride doped with europium at 128 degrees of Celsius. In the mid-range, cadmium tungstate performs much better compared to calcium fluoride doped with europium. Concluding, in this research, we compared the effect of temperature on the luminescence efficiency properties of two single crystal scintillators for applications in harsh environments. The high density of cadmium tungstate compared to calcium fluoride doped with europium and the luminescence signal of this material make it suitable, besides medical imaging, also for high energy physics and applications of scintillators at harsh environments. The resistance to high temperatures is of extreme importance to various applications. For example, in space exploration, spacecrafts are extremely resource limited in both mass and power. Spacecrafts which approach the vicinity of the Sun will face harsh environments regarding the onboard instrumentation. Only radiation-hard detectors that need little or no cooling at all will be able to successfully operate after long cruising times and during the expected mission lifetimes.